Let's have fun. Okay. All right, let me start the slide. All right, here we go. Okay, so again, here actually what I'm going to do is I might go a little bit faster than I normally would, mostly because today it's really just review. It's stuff you probably have seen before. If you do want more practice with it, you're more than welcome to contact me and see me during office hours. You know, I'll be more than happy to see you then and do more examples with you. So anyway, what I'm going to start doing here is some notation. Now in this class, the book does it. You're actually going to have to deal with what's called a set. And basically a set, there is a lot of theory there, but it's really just a fancy word for a collection. Okay? Wait, can everyone see the, oh no, I forgot to share it, I'm sorry. Application. Here we go, let me share that. Okay, can you see it now? Yeah, I'm sorry about that. Okay. But again, a set is just a fancy word for a collection. I mean, the book goes into the theory a lot more, but I'm not really going to get into the theory as much as the book does. But that's just what a set is. It's just a fancy word for a collection of things. And there is some notation with a set. For instance, here, you can denote a set using these curly braces. And you could separate and list the elements, separating them using commas. With a set, though, you don't list an element more than once. So in other words, there's no repetition in a set. Okay, and now sometimes you'll see, as you'll see today actually, sometimes there's way too many elements to list. And so when that happens, what we can do is we can use this ... notation. The idea there is you list enough elements so that the underlying pattern is easy to see. In other words, you can tell what the next item in the set is. So for instance, if you consider the natural numbers, right? These are the natural numbers. This is an example of a set. It's really just the positive integers. Let's see, what's the map? Oh, there it is. So for instance, we have 1, 2, 3, 4, but after 4, right, the next element would be 5. Hopefully you can see that, right? Because the pattern is obvious. You just keep on adding 1. And the natural numbers for us is just the set of positive integers, right? So we really have to use the ... notation because there's infinitely many positive integers. I also listed this set because some books allow 0 to be a natural number, but the authors here do not do that. So when you see natural numbers, just think positive integers. Okay, so that was one set. Another one is the integers themselves. This is how the author listed it. I mean, this is a little strange, I know, because he has the ... on either side. I mean, what I did was, hopefully it makes more sense if I did it this way. I wrote the set this way, as you can see. Right? So we have, so basically with the integers, you have the natural numbers, okay? Which for us are positive integers. You throw in 0, and then you negate the natural numbers. That's really what the set is. Hopefully here, in the way I listed it, you can see what the underlying pattern is. So the next one would be 4, then -4, 5, then -5, and so on. That's all. But these are just some sets that we're dealing with. Now, another set that we're going to deal with is the rational numbers. In other words, the fractions of integers. So again, this is when you have all these fractions, but you have an integer on top as the numerator and a non-zero integer down here. Okay, so you have an integer on top, a non-zero integer here. These are the rational numbers. All right, so is everyone with me?
Yeah.
Okay. I know I asked that a lot, I
Yeah.
know. Okay, so let's get to some more notation. Now, not every number out there is rational though. In other words, there's a lot of numbers out there that are not rational. We call those numbers irrational numbers. I put some examples here. I put pi, for instance, that is the number that pi represents. You know, you probably have seen it in formulas for circumference and area of a circle. Like for circumference, you have pi times the diameter. The number that pi represents is actually irrational. I wrote it here as an approximation, 3.14. You might have seen the number that e represents. If you haven't, that's okay, but it turns out there's a famous number. You'll see if you take calculus or even pre-calc, and the number that e represents is about 2.718. It turns out to be irrational. But there's lots of other irrational numbers. You'll see more actually when we do square roots. But there's rational and there's irrational numbers. Those numbers together form the real numbers. So this is going to be our playground, so to say, the real numbers. And these are the numbers you probably have seen. These are the numbers you've seen many times, probably. It's just the set of all numbers that are rational or irrational. So that's what the set of real numbers is. Now, there's an even bigger set, though. I'm not sure if we'll get to it, but at the very least, I'm mentioning it now. It's the set of complex numbers. Those numbers are numbers in this form. They're a plus I times b, where I, by definition, it's the square root of -1. Or if you don't know what this notation is, I mean, we will get to it. It's a number whose square is -1. And right, there's no real number that can pull that off. So that's why the complex numbers is a bigger set. I mean, we might get to that, we might not. In the past, I've never been able to cover the complex numbers, but we'll see. Okay, so that's just some notation I wanted to present. Now we get to do exponents. So now what we're going to look at are stuff with exponents. Again, I might go a little bit faster than I usually do because this stuff you've seen before. So I treat this like review. But again, if you do need more help with it, don't be afraid to contact me. So for any real number a, right, and any positive integer n. So in other words, we're going to say what it means to take that number a and raise it to the n power from a. We're going to raise it to the n power. N again is a positive integer. And this is what you mean. This is what we mean that is. It's just a times itself n times. In other words, we're going to get n copies of a. And we multiply them together. In particular, when n is 1, we have this. So a to the 1 is just the number itself. A to the n, you're multiplying a by itself n times. So that's just what happens with exponents. And this is just some terminology I presented. A to the n, we call it the nth power of a, or you might see it as a raised to the nth power. And I didn't put this on the slide, but the a here is the base. The n here is the exponent. The a is called the base, n is called the exponent. So that's what happens here. And these are just some examples I threw in there for fun. You know, for instance, we have 4 is 2 times 2, which is 2 squared. And 81 is just 3 raised to the 4th. 3 to the 4th is 3 times itself 4 times. That is, excuse me, you're multiplying 4 copies of 3 together. Yes, that's good. Now, we do have to be careful because what if the base is negative? I mean, if you saw those examples from before, the base, the a, was positive. Well, if it's negative, you have to be a little bit careful because you can have something like, well, you'll see what I mean. So if you have negative 3 squared, right, that's just negative 3 times itself, which we know is 9. Well, what if I wrote it this way? Well, notice here, there's no parentheses here. But this is not the same as this. Here, I'm multiplying negative 3 times itself. Here, I have a negative, but I'm multiplying 3 by itself. So I get negative 9. What am I trying to say here? Well, you have to be careful when the base is negative. You have to use your parentheses carefully. That's what I'm trying to say. Okay? That's what I'm trying to say. I mean, if the base is positive, so if instead of negative 3, we had just 3, then you really don't have to worry because the negative sign's not there. But here we do have to be careful. So that's really all I'm trying to say here. See, I'm saying it again. Okay. All right. So let me keep going. Okay, so we had positive exponents, right? We had that. Well, now let's take a look at negative exponents. Here, those you'll see our base has to be non-zero. And you'll see why, actually, because what does it mean to do a to the negative n, where n, again, is a positive integer? So we have a to a negative exponent. You do 1 over a to the n. So basically, if you have a negative exponent, you take the negative sign away, but you do 1 over. That's what I'm trying to say here. Okay. But you can see, hopefully you can see why a has to be non-zero, because you'll see, I think it's on the next slide actually, you'll see that if a were 0, this would be 0. We don't divide by 0. You never divide by 0. And it turns out for this, and we'll see later on a proof, any non-zero number raised to the 0 is 1. So a to the 0 is 1 if a is not 0. So I just put in 2 examples here as well. 2 to the negative 2, right? That's 1 over 2 squared. Okay, which is 1 over 4, right? We do 1 over. When you do 1 over, that takes away the negative, right? 3 to the negative 5, it's 1 over 3 to the 5, which is this. All right, that's good. Let me just say explicitly what happens when the base is 0. Well, in particular, 0 to the n, that's just 0, if n is a positive integer. I mean, you should expect that because all you're doing is you're multiplying 0 by itself n times. And 0 times anything is 0. But again, what happens if the exponent were negative? Well, that's not defined. Mostly because you can't divide by 0. You cannot divide by 0. Excuse me. And in particular, this is something else I wanted to point out. 0 to the 0, it's not 1, it's not 0, it's nothing. 0 to the 0 here is not defined. Okay, let me just pause this. Okay, I just want to pause the recording for a second so it doesn't get too big. So not stop sharing.